In this video, we're going to talk about intermolecular forces, and in order to understand these, make sure that you have watched the video on polar and non-polar molecules and the bonding continuum. Okay, so when it comes to intermolecular forces, we need to know that covalent molecules, that is, whether they're covalent diatomic gases or some of those bigger covalent molecular solids, such as S8P4 and C60, like fullerene, they have their low melting and boiling points due to having weak intermolecular forces. And intermolecular forces are attractions between molecules. So you cannot have an intermolecular force if you only have one atom or if you only have one molecule. You need at least two molecules to exist, and then you can draw an intermolecular force between the two of them. We also need to have an awareness that historically intermolecular forces have been called van der Waals forces. So if you're reading a past paper question, or if you've got a sort of like revision guide or any sort of textbook and it talks about van der Waals forces, they just mean intermolecular forces. So here we've got monatomic gas, and just showing you that the intermolecular forces are things that we draw between the atoms or molecules. They don't exist until we put molecules beside one another. Now, there are three types of intermolecular force. All of them are very weak. Okay, we will be talking about some of them being a lot stronger than others, but all of these intermolecular forces are very weak when we compare them to covalent bonds, ionic bonds, etc. The three types of intermolecular forces are hydrogen bonds, which we can shorten to H bonds, something called permanent dipole interactions, which we can shorten to PDIs, and then we have London dispersion forces, which we are allowed to shorten to LDFs. In terms of strength, hydrogen bonds are the strongest type of intermolecular force, and London dispersion forces are the weakest. But again, all intermolecular forces are very weak when we compare them to covalent bonds or ionic bonds. So we're going to focus firstly on hydrogen bonds and permanent dipole interactions because they are very similar to one another. So these types of intermolecular forces only occur between molecules that are polar. Okay? You cannot have hydrogen bonds, you cannot have permanent dipole interactions in molecules that are non-polar. And remember, when we have a polar molecule, we can draw on a dipole, or what is called a permanent dipole. So remember, within the molecule that is polar, there's one bond, maybe more than one bond, onto which you can draw a delta positive or a delta negative sign on atoms. When we talk about hydrogen bonds and permanent dipole interactions, what we mean is that the delta positive atom on one molecule has an attraction to the delta negative of a different molecule. So here we have two acetone molecules, and what we've done is we've drawn on the delta positive, the delta negative on the dipole, and where we have a delta negative on one, we can draw an attraction between it and the delta positive on a different molecule. Remember that intermolecular force only exists between the molecules. And then we've got another example, we've got methanol, and again, methanol is a polar molecule. The oxygen-hydrogen bond is polar, and we can put the delta negative on the oxygen, delta positive on the hydrogen, showing our intermolecular force. It goes from the delta negative of one molecule to the delta positive of another molecule. Okay, so this is what we mean by intermolecular forces, hydrogen bonds, and permanent dipole interactions. It is always between the delta negative of the dipole on one molecule to the delta positive of the dipole on another molecule. So that is the similarity between them. We need to know what makes something a hydrogen bond and what makes something a permanent dipole interaction. So if the polar bond in the molecule is an OH bond, a hydroxyl group, or an NH bond, or an FH bond, if the polar bond is one of those three bonds, then we say that it's going to be a hydrogen bond. We call the intermolecular force a hydrogen bond. If it is any other bond than one of those three bonds that makes the molecule polar, then we call it a permanent dipole interaction. Okay? So firstly, if you've got a polar molecule, it's going to either form hydrogen bonds or it's going to form permanent dipole interactions. If you can see within the molecule an OH, NH, or FH, then you can say it forms hydrogen bonds. If it's polar and you don't see any of those three bonds, then it's going to be permanent dipole interactions. So what we've got is a few slides with molecules, and it's about identifying does it form hydrogen bonds, does it form permanent dipole interactions, or will it form neither? If you want to just skip ahead, if you don't want to do the practice questions, you understand this, absolutely fine. Here's our first molecule. Do you think hydrogen bonding, permanent dipole, or neither? Well, this one, it's not symmetrical. It does have a polar bond because it has that OH bond, and OH is one of the three bonds which allows that molecule to do hydrogen bonding. Second molecule here, if we look through that, try and make your decision. Well, in this one, it's only made of carbon and hydrogen, and hopefully from last video you remember that if something's made of only carbon and hydrogen, we consider it to be non-polar. So this is not a polar molecule, so it will not form either permanent dipoles, or hydrogen bonds. This next molecule is part of a polymer, and I want you to look at the bonds in it, and do you think it will have hydrogen bonding, permanent dipole, or neither? Well, hopefully you've identified that that is a polar molecule. It's not symmetrical, and the carbon-bromine bond is polar. Carbon-bromine is not one of those three bonds which allows a molecule to form hydrogen bonds. It's not an OH, an NH, or an FH. So that one has permanent dipole interactions. Here, we've got silicon in the middle with 4 chlorines around it. Does that form hydrogen bonding, permanent dipole interactions, or neither? Hopefully, you've identified that that is a symmetrical molecule. It is a tetrahedron. Therefore, it's non-polar and will not form any of those interactions. We've got a molecule here. What do we think? Well, this molecule, it is polar. It does have a polar bond. The carbon-oxygen bond is polar, so it will form one of them. But it doesn't have an OH, it doesn't have an NH bond or an FH bond, so it has to form permanent dipole interactions. And the carbon-oxygen bond is the polar bond. The carbon would be delta positive, the oxygen would be delta negative. We've got one here. What do you think of that? Well, this one, we have got the OH bond, which would allow us to form hydrogen bonding, we've got the C double bond O, which will allow us to form permanent dipole interactions. So that one is capable of both. If you see anything like that with like a hexagon on it, that hexagon is just made of carbon and hydrogen. So you can forget about that when thinking about whether or not something is forming hydrogen bonds or permanent dipole interactions. So we now know the difference between hydrogen bonding, permanent dipole interactions, and can identify if a molecule has one or the other, if it has both or if it has neither. We have a third type of intermolecular force called London dispersion forces. And this is quite difficult to describe, but you can be asked to explain how they arise. So the first thing we need to know is that every single molecule, whether it's polar or non-polar, and monatomic atoms, all of them can form London dispersion forces. However, if something is a covalent network, a metal, or an ionic compound, they will not form London dispersion forces. Okay, London dispersion forces are intermolecular forces, so you've got to be a molecule or monatomic. And London dispersion forces are the weakest type of intermolecular force. However, the more electrons a molecule has, in other words, the bigger a molecule is, the London dispersion forces will get stronger. How do London dispersion forces arise and what are they? So it goes back to thinking about an atom. Atoms have their nucleus surrounded by electrons, and those electrons are constantly moving around. And this means that if you were to take a snapshot of an atom at any given second, you would have temporarily more electrons on one side of an atom compared to the other. And we would describe that as an uneven distribution of electrons. Now, whichever side of the atom has more electrons would be slightly negative, and whichever side had less electrons would be slightly positive in comparison. So one side would be delta negative, one side would be delta positive. And we call this thing that happens for just a fraction of a second a temporary dipole. So in terms of like an image, we go from a completely neutral atom to, due to the electrons moving around, an atom that has a delta negative side with slightly more electrons and a delta positive side that has slightly less electrons. If we were describing this process in a sentence, we would say that an uneven distribution of electrons creates a temporary dipole. What happens next is something called an induced dipole. And that is that the temporary dipole that you formed will have an effect on neighboring atoms or molecules. And it can turn atoms that are not dipoles into dipoles. So if an atom is being turned into a dipole, it's called an induced dipole. So whenever we put our temporary dipole next to another atom, it will turn that atom into a temporary dipole. And then the attraction we have between the temporary dipole and the induced dipole, between the delta negative and the delta positive of different atoms, is what we call a London dispersion force. So the London dispersion force is the attraction between delta positive of one atom and delta negative of another atom. Now, as we said, the number of electrons in an atom or molecule affects the London dispersion forces. And that is because in order to create your temporary dipole, you need to have an uneven distribution of electrons. The more electrons an atom or molecule has, the more easily you can create an uneven distribution of electrons, the higher the probability there is. And this means that as molecules get bigger and bigger, these temporary dipoles get more common. And therefore, you're going to have stronger or more frequent or a higher number of London dispersion forces in bigger molecules compared to smaller molecules. So what intermolecular forces can different molecules form? So just to summarize, if something is a non-polar molecule, so if it has no polar bonds or if it is symmetrical, the only intermolecular force you can form are London dispersion forces. If a molecule is polar and the polar bond is an OH, NH, or FH, it can form hydrogen bonding, but also remember it can also form London dispersion forces. Don't forget about London dispersion forces in things that can form hydrogen bonds. And then finally, if a molecule is polar, but it does not have an OH bond within it, an NH bond within it, or an FH bond within it, what it can do is form permanent dipole interactions, and also London dispersion forces. So you need to understand what each of those intermolecular forces are and then be able to identify from a molecule what forces it would have. And that will lead us to being able to talk about the properties that molecules will have based on the strength and number of intermolecular forces they have.